Hi, my name is Tom Heffel, and this channel is all about helping students learn chemistry. In this video, we're going to introduce the idea of buffered solutions. And what a buffered solution is, it's a solution that contains both acid and base. However, there's a big must here. That acid and base, they need to be acid-base conjugate pairs. So if you have an acid, you need to have its conjugate base in order for it to be a buffered solution. And if you have a base, you need to have its conjugate acid if it's going to be a buffered solution. We're going to do 3 problems. Okay, now this first problem, we're going to put 0.25 moles of just acid in to the solution of a 1 liter solution. So this is not a buffer. However, the next 2 are buffers. Okay, so I'm going to mix hydrofluoric acid with its conjugate base, which is the fluoride ion, of which I'm going to get in sodium fluoride. And the next one's going to be a buffer as well. It's going to be acetic acid, okay, which has the acetate ion. So if I put a salt in there with the acetate ion, I'll get its conjugate base. So acid, conjugate base, acid, conjugate base. And if we have both the acid and conjugate base, that's what makes these last 2, okay, buffers, okay? And what I'd like to do is I'd like to start out with something that's not a buffer so that we can kind of compare and contrast what a buffer is versus what a buffer is not, okay? So let's start out the one that is not a buffer, okay? So if I put 0.25 moles of HF into a 1 liter solution, basically I have a molarity of 0.25 HF. And I simply just need to calculate the pH, okay, if I'm given the Ka. So this first problem, if I was to write out a prompt, okay, would look something like this. Okay, so if you want to pause the video and kind of write that prompt down, just so that you know what we're talking about here. So we have the Ka value. It's going to be 6.8 times 10 to the negative 4. So let's go ahead and do this problem that's not a buffer. So we're just going to write a good equation, HF, okay, and if it's in water, it's going to end up being in equilibrium with hydronium ions and fluoride ions. And I'm just going to do an ice chart. I'm going to plug in the molarity. Remember, 0.25 divided by 1 will give me the molarity of 0.25 molar. We don't worry about water when it's in an equilibrium problem because pure liquids aren't included in the equilibrium expression. And we simply say, hey, this is going to go down X, this is going to go up X, this is going to go up X, this is 0.25 minus X, this is X, and it's all dictated by the Ka value, which was in our prompt as 6.8 times 10 to the negative 4. So what I'm going to do is I'm going to set up the equilibrium expression. Ka is equal to hydronium times fluoride all over HF, and that's going to be equal to that number, 6.8 times 10 to the negative 4. And what I'm going to do is I'm going to substitute these numbers in here for these places in the equilibrium expression. But I'm going to do the approximation method, because if this is times 10 to the negative 4, that means this shift over is going to be really small. So if I have 0.25 minus a number like 0.0001, okay, it's going to be approximately 0.25. And by doing that approximation method, we eliminate having to use the quadratic equation. And this is a perfectly legal move in chemistry problems. Okay, so what I'm going to do is the H3O at equilibrium is equal to X. The fluoride ions are also equal to X. The hydrofluoric acid is 0.25. And that's all equal to 6.8 times 10 to the negative 4. Okay, so I'm going to cross multiply. I'm going to get X squared equal to 0.25 times 6.8 times 10 to the negative 4, and then solve for X. So I'm going to take the square root of both sides. And when I do that, I get this X equal to be 0.013, okay? So this is pretty small relative to the value of 0.25, and that's why the approximation method is okay. Okay, well, this X value is actually equal to the concentration of the hydronium ions, okay? It's also the fluoride ions, but I'm really interested in finding the hydronium ions if I'm trying to find pH, because pH is simply equal to the negative log of the concentration of the hydronium ions. And if this is the value of the hydronium ions, I'm going to plug it in, and I'm going to find out that my pH is going to be equal to 1.88. Okay, so this is a problem that is not a buffer, and I want to kind of compare that to something that is a buffer. Okay, so as you can see in this ice chart, we only had the acid. Okay, the conjugate base, fluoride ion, there was nothing present in the beginning. Okay, so this is not a buffer. Okay, the next problem though is going to be a buffer, because in my container, okay, I'm not just going to have 0.25 molar HF, and that's kind of like what I had over here. I just had a container of 0.25 molar HF, but I'm going to have the 0.25 molar HF, and I'm going to have 0.25 molar sodium fluoride. Remember, 0.25 moles divided by 1 liter is going to tell me that my molarity is going to be 0.25 molar NaF. Okay, so the only difference between these two is this idea that I got some 0.25 molar NaF, or sodium fluoride. So how are we going to deal with the sodium fluoride? We got to kind of deal with that part first. Okay, so I'm going to write a good equation for sodium fluoride. When it's in water, it actually ionizes 100%. So I am using a single arrow to show that it's a complete shift over. And since it's a complete shift over, I tend not to use ICE, initial change at equilibrium, because there is no equilibrium because of the single arrow. So I like to call these things BCAs, which means before change and then after the change. Okay, and that's what we need to look at. Okay, so if I have 0.25 molar in here, I know all of this is going to shift to the right. There's nothing to begin with, but it's going to shift all the way to the right. So this is going to go down 0.25, and there's going to be no sodium fluoride left inside the solution. Instead, they're all going to be ions of sodium and fluoride. Now, the sodium ions is a conjugate acid of sodium hydroxide. So if I wrote that down really quick, sodium hydroxide creates these ions, right? And I have this ion of sodium in here, okay? However, if sodium hydroxide is a strong base, then this acid, its conjugate, is negligible. So we got a negligible acid that has no effect on pH. And since there's no effect on pH, I don't really worry about those ions at all, okay? Now, the fluoride ions come from the weak acid, hydrofluoric acid. Right? So we have these ions right here. Now, hydrofluoric acid is what I call a weak acid, WA for weak acid. And if it's a weak acid, then its conjugate is going to be a weak base. Now, that's important because that will affect pH. So I am interested in the concentration of these fluoride ions that are in solution with my HF, okay? And I think about it a little bit more, hey, HF, an acid, and its conjugate base, well, that's what makes up a buffered solution. We have acid and base both present, and they must be conjugate acid-base pairs, okay? That's what makes the buffer, okay? So I'm going to write the same equation that I have here, over here, HF plus water in equilibrium, with hydronium ions and fluoride ions. I'm going to set up my ice chart, and I'm going to plug in the 0.25 molar of HF right here. Remember, I don't worry about the water, okay? But I do have fluoride ions. They're in a concentration of 0.25. So I'm going to take those and place it right here, okay? So this is the difference between a buffered solution and a non-buffered solution. The non-buffered solution doesn't have anything over here, okay? Where the buffered solution is going to have both the acid and its conjugate base present at the same time. And that does something to the equilibrium that we're going to talk about here in a few minutes. But I'm going to set up the chart, okay? Same way, this is going to go down x, this is going to go up x, this is going to go up x. So this is 0.25 minus x, this is x, and this is 0.25 plus x. Now, if this shift is small, we can still do the approximation here and over here. Because if 0.25 minus a very, very small number is approximately 0.25, well then 0.25 plus that same exact small number is going to be approximately 0.25. So definitely okay to approximate in both places. Now remember, Ka is equal to the products divided by the reactants. We don't include water in that equilibrium expression. So we get something that's like this. And it looks exactly like the same as the last problem. And that's all going to be equal to 6.8. Yeah, 6.8 times 10 to the negative 4. And we're going to do our substitution. We're going to put in x for hydronium, 0.25 for fluoride, and 0.25 for hydrofluoric acid, which is equal to 6.8 times 10 to the negative 4. Now, here's the idea of actually, let's solve for the x first. So we're going to cross multiply. Okay. In fact, both of these cancel each other out. So x is equal to 6.8 times 10 to the negative 4. Look how much smaller that shift is than 0.013. And this is what I want to talk about, like kind of like what a buffer is. Okay. So over here, okay, we initially start out with nothing over here. Okay. And we have a whole bunch of reactants. So we know that there's going to be a shift. That shift is going to be small because it only needs to equal this number, 6.8 times 10 to the negative 4. Okay? Well, in a buffered solution, we already have a number here. We already have stuff present over here. So this shift is going to be even smaller, and it's going to end up being 6.8 times 10 to the negative 4. And I kind of have a silly analogy to kind of talk about this, but I hope it hits home and I hope it makes sense to you, okay? So think about like a club where there's a whole bunch of people that are waiting to get into the club, okay? And there's this guy with the rope that allows so many people through, okay? When you have a non-buffered solution, okay, you got all these reactants, all these people waiting outside to get into the club, okay? Now, it's a small club because the Ka value is pretty small, okay? But there's nobody there. So initially, the doorman opens up the rope and says, come on, people, get into the club, right? Okay? And then when it hits that 6.8 times 10 to the negative number, he closes it off and nobody else is allowed to come in unless another person comes out, okay? And that's kind of like how a non-buffered solution works. Nobody in the club initially. The way a buffered solution works is that there's people in the club already. There's still the same amount of people waiting outside, but the club is already kind of full, okay? So the doorman is going to say, okay, just a couple people in, and then I'm shutting it off immediately, okay? Unless another person comes out, and then you establish your dynamic equilibrium, okay? So if a small amount of people come in, that's why this shift is so small. Now, I know that analogy is a little silly, but hopefully that kind of makes sense to you, okay? Now, to finish off this problem, if this X value is the concentration of hydronium ions, we just got to take the negative log of that, because remember, pH is equal to the negative log of the concentration of hydronium ions. If we plug that in there, we will find out that we get a pH equal to 3.17. So the pH is a little bit higher because there's some base present, okay? No base present, you get a pH of 1.88, okay? If you add a little bit of base to it, obviously the pH is going to go up a little bit. It has a pH of 3.17, okay? The last problem I'd like to see if you guys can do on your own, it's problem number 3 right here, okay? So if you'd pause that video, okay, when you come back, I'll be working on this problem. And this problem, see if you can do one completely on your own, and that's when we have 0.25 moles of acetic acid with 0.1 moles of potassium acetate, which is the conjugate base. So let me erase all of this, and we will get into that last problem, which is a buffered solution. Okay, so here we go. The first part that we're going to take care of is the salt part. Okay, so potassium acetate is going to ionize 100%. So we're going to do a BCA, okay? And if we start out with 0.1 moles divided by 1 liter as 0.1 molar, okay? Remember, all of this is going to go away, okay? So all 0.10 is going to react, and it's going to all push over to the other side. So in the end, we get 0.1 molar of potassium ions, which actually have no effect on the pH because potassium is the conjugate acid of the strong base potassium hydroxide. Okay? However, we have acetate ions, which is a conjugate base of a weak acid. Okay? And if you have a weak acid, its conjugate is going to be weak as well. So it does have an effect on pH. Okay? This is actually the conjugate base of acetic acid, and that's what creates the buffered solution. So what I'm going to do is I'm going to take acetic acid and write an equilibrium expression for it. Okay, acids donate protons to form hydronium, and that's going to leave over the acetate ion. I'm going to do an ICE, and I'm going to put the molarity of the acetic acid. Remember, 0.25 moles divided by 1 liter tells me that the molarity is 0.25. We don't know anything about hydronium, but we do know that the conjugate base of this acid is present, and it's present because of the salt. When it ionizes, we get 0.1 molar of the acetate ion, and we have the acid and the conjugate base both present at the same time. And acid-base conjugate pairs, they don't react with each other. They're in equilibrium with each other. Okay? If I ever had an acid and base and they were not conjugate pairs, they would react with each other. Okay? But if they are conjugate pairs, they're in equilibrium with each other. Okay? So I'm going to finish up my ice chart by saying that this is going to go down x, which is 0.25 minus x, or approximately 0.25, because the x is going to be small. This is going to go up x, this is going to go up x, x, and 0.10 plus a small number is still going to be approximately 0.10. Now, in the prompt, it said that the Ka value is equal to 1.8 times 10 to the negative 5. And all I'm going to do is set that 1.8 times 10 to the negative 5 equal to the products over the reactants. So the products are going to be x and 0.1 over the reactants, which is 0.25. I'm going to do some cross multiplication to solve for x. X comes out to be 4.5 times 10 to the negative 5. 4.5 times 10 to the negative 5. And that's equal to the concentration of hydronium ions. So if I take the negative log of the concentration of hydronium ions, and I plug that in, I'll get my pH equal to 4.35. So hopefully you got to 4.35 as that practice problem. If not, keep working. And with time and effort, you'll understand buffered solutions. If you like this content, please give a like and subscribe. And when you add that comment, it does push off this information to other students that are interested in learning chemistry.